Let us look at some numericals. Example 1 says the resistance of a conductor is 10 ohm at 20 degree Celsius. What will be its resistance at 100 degree Celsius if temperature coefficient of resistance is 2 into 10 power minus 3 per degree Celsius. Now here let us take this as a reference temperature and this as a reference resistance at reference temperature. So we know the form where R is equal to R naught into 1 plus alpha into delta T. Now this R naught is given as 10 ohm into 1 plus alpha is given as 2 into 10 power minus 3 into delta T, which in this case would be difference of 100 degree Celsius minus 20 degree Celsius. Keep in mind that here alpha is also in per degree Celsius only, so difference here also would be in per degree Celsius only. That is equal to, it is 10 into, it's 1 plus, so 2 into 80 is 160 and 160 into 10 power minus 3 would be 0.16, that is 10 into 1.16, that is equal to 11.6 ohm. So as seen or as expected, the temperature has increased. The resistance has increased because temperature also has increased. Example 2 says, at what temperature would the resistance of a silver conductor be double its resistance as 20 degrees Celsius? Temperature coefficient of silver is given as 3.8 into 10 power minus 3 per degree Celsius. Now what is given here is, it says, question says to find out at what temperature will the resistance become double at a reference temperature, which means here the form what we know is R is equal to R naught into 1 plus alpha into delta T. Here R, which is resistance at a higher temperature, this R is equal to 2 times R naught. So putting it back here, what we get is, we get 2 R naught is equal to R naught into 1 plus alpha into delta T. From here this R naught gets cancelled, so what remains is 2 is equal to 1 plus alpha into delta T. Bring this side, 2 minus 1 is equal to alpha into delta T, but 2 minus 1 is 1, so alpha into delta T is equal to 1, or delta T is equal to 1 by alpha, and the value of alpha is already given as 3.80 into 10 power minus 3, so it will be 1 by 3.8 into 10 power minus 3, that is delta T would be 10 power 3 by 3.8, and that is equal to, if we solve and see, that's equal to, it will be 263.158 degree Celsius. This is what delta T itself is, but this is nothing but T2 minus T1, which is 263.158. If you write from here T2 alone, so T2 is equal to T1 plus 263.158, and T1 was given as 20 degree Celsius. So putting it back here, T2 is equal to 20 plus 263. You can write 1516 to make it more simpler. So T2 is equal to 283.16 degree Celsius. So this is the required answer. Example 3 says the temperature coefficient of resistance of a wire is 12.5 into 10 power minus 4. At 300 Kelvin, the resistance of the wire is 1 ohm. Find the temperature at which resistance will be 2 ohm. Now here again, using the same form, we know R is equal to R naught into 1 plus alpha into delta T. Here we need to find the temperature. Again here R naught is given as 1 ohm and R is given as 2 ohm. That's 1 plus alpha and delta T. We'll put the values of alpha and solve later. We'll first solve this basic part. So 2 is 1 plus alpha delta T. Again here alpha into delta T is equal to 1, or delta T is 1 by alpha, which here in this case is 1 by 12.5 into 10 power minus 4. That goes on top, that is 10 power 4 goes on top, so it becomes 10 power 4 by 12.5. That's equal to 800. Now here, since one temperature is in terms of Kelvin, it's in 300 Kelvin here, you can write this also in terms of Kelvin only. Keep in mind that the change in temperature is same in both the scales. So write this as 800 Kelvin, or this is nothing but T2 minus T1 is equal to 800, or T2 is equal to 800 plus T1, and T1 was the early temperature, which was 300 Kelvin. So T2 is equal to 800 plus 300, or T2 is equal to 1100 Kelvin. Example 4 says, find the resistance of a hollow cylindrical pipe of length 1 meter whose inner and outer radii are 10 centimeter and 20 centimeter respectively. Assume that the cylindrical pipe is made of a material of resistivity 2 into 10 power minus 8 ohm meter. So there is a cylindrical pipe which has an inner and outer radii, something of this kind. So this length is given as 1 meter. So this length is given as 1 meter. Current may enter from here and leave from this side, or vice versa. So current conducts here. Now we need to find what is its resistance. So resistance is given by R, which is given mathematically as rho L by A. So here should keep in mind that this is the area where electrons will flow. This is a conducting part. So we need to find only this area. Now to find that area, A is equal to, if you look at this, there are two cylindrical regions of radius R1 and outer as radius R2. You want only this area, so it is called the area of inner part as A1 and outer as A2. So it will be A2 minus A1, because you want only this region. I'm calling the area of inner cylinder as A1, the area of the whole thing as A2, and then what we want is only this region. So that will be A2 minus A1. So A is equal to, it will be pi into R2 square minus pi into R1 square, and that would give us A is equal to pi into R2 square minus R1 square. That is equal to pi into R2 would be the bigger radius, which is 20 centimeter. So 20 into 10 power minus 2 whole square minus R1 is the inner radius, which is 10 into 10 power minus 2 because it is given in terms of centimeter, and this is equal to, it is pi into, this would be 400 minus 100 into 10 power minus 4. Our area is equal to 300 pi in 10 power minus 4 meter square. Now we need to find what is the resistance. So R is equal to rho is 2 into 10 power minus 8 into length of the cylinder is given as 1 meter by, it is 300 pi in 10 power minus 4. It gets cancelled here, 10 power minus 4 gets cancelled. So what remains here is 10 power minus 4 remains. So 2 ones are 150s are, and if we solve and see this, then what we get from here is R is equal to, it will be 2.12 into 10 power minus 7 ohm. So this is a required answer.